Hello everyone. This is um, Fundamentals of Compressible Flow course being conducted by NPTEL, and we are in the seventh live tutorial session of this course. And the heading of this particular course is Expansion Waves and Oblique Shocks dash Analysis. So in the previous week lectures, we saw the modeling of expansion waves and oblique shocks, and in this current week content, we learned about the analysis part of these expansion waves and oblique shocks. So we shall uh, discuss few questions related to this particular topic, and we shall start in few minutes, right? And the instructor of this course is Professor Niranjan Sahu from IIT Guwahati. And my name is Aditya Sharma, and I am a research scholar from IIT Guwahati only, and your TA for this tutorial session. Thank you. So we will start today's session, all right. So as I've already told that this session shall be catering to the analysis part of the expansion waves and the oblique shocks, which are essentially encountered in supersonic flows. So what is an expansion wave and what is a oblique shock? So that has been covered in the previous week's content. So briefly, if I should tell, so expansion wave happens when we move this flow away from itself, and when the flow is being moved towards itself, in that case we call this sorry uh, in that case we call it an oblique shock. All right. So so in what we have been doing in these tutorials, how we are conducting these tutorial is, first we go through the topics that have been covered in these uh, lectures, in this particular lecture. So uh, at present we are in this week 7 lecture. All right, so related to that week's content only, we are conducting this particular tutorial session. So I was telling that what we have been doing is, first we go through the topics that have been covered briefly, just brush up the topics that have been covered in a particular week sorry week's content. And then after that we try to see some conceptual and numerical questions based on the content of that particular week. So in this uh, session also we shall proceed in that manner only. All right. So in this week 7, there were two lectures. So first lecture was lecture 16, and then there was another lecture, lecture 17. Right. So first major topic in this particular session was oblique shocks. Right. So as I just mentioned that if we see here, right. So oblique shock is nothing but, so let us suppose this is some wall, right, and there is flow moving in this direction, right, from left to right with some Mach number m. So if we move this flow towards itself, right, so how do we do that? By deflecting this flow, right. So we keep some wall at an angle to the this upstream flow, and then by virtue of that deflection, what we see is this phenomenon, right, which is nothing but oblique shock. The direction of the flow will be parallel to the this wall that has been kept for deflecting the flow, but then there will be this shock that is at an angle to this upstream flow, right? So that angle is denoted by beta, and we call that angle as this shock wave angle, right? And this deflection angle we denote by theta. Nomenclature I am just briefing. All right. All right. So this is about oblique shock. So this has been covered in previous uh, lectures or previous week's content, right? And then there is very next topic is this theta beta m relation, right? There's this theta beta m relation, which is nothing but there is one formula, right? So which relates theta beta and m. So we have seen this uh, formula in this or this equation we have seen this relation we have seen in previous week's content, right? So I haven't noted down in this particular for this particular week's session, but then we are aware of this expression or relation, right? So on the basis of this particular relation, we obtain a curve, and based on that curve, some inferences have been deduced, right? So first, let's see what this curve looks like, right? And then we shall later see what are the peculiarities of with uh, related to this in relation to this particular theta beta m curve, right? So if we see theta beta m curve, right? So it is something like this. Here we keep theta on the y-axis, right? And in the x-axis we keep this, right? So it looks something like this. Right? Something like this. It's something like this, right? So if you see this curve, let's say this is 0 degrees, this is 50 degrees, and this is where this is 90 degrees, right? So I have already drawn this theta and beta uh, uh, with respect to the oblique shocks, right? So if you see, let's say, so these drawn things are the curves, right? So these are the theta. These curves are for a particular Mac value. So if I take this particular case, this is for some Mac value, right? And this is for some another Mac value, and then same in the same way, this curve is for some particular uh, Mac value, and this is for some another Mac value, right? But if you take one curve at a time, so let's take this last one curve. So if you take this curve, you see, so this curve has some limit for theta, right? And if you see this particular curve, you see the case is also same for this particular curve, and the same is for this curve, and then also this curve. So what this curve shows is that there is a particular value of theta beyond which we cannot get solutions of this oblique shock. All right. So that is the thing this particular curve is trying to propagate, right? So in that case, we won't get any solution with respect to a particular given parameters, right? All right. So one another thing is that when there is this uh, oblique shock, right? When there is a deflection of a particular flow. So in that case, if we take this theta beta m relation, so we get two solutions because m has the Mach has the power of 2. So in that case, which basically means that we will have two solutions of Mach, right? So these two solutions correspond to the strength of the oblique shocks, right? So in that case, we get two solutions. One is this strong oblique shock, right? And then another is weak oblique shock, right? So if you see this particular graph, right? So if we take, let's say, let's just number these curves, right? 2, 3, and 4. So if you take this curve, if you take, let's take curve 2, right? Let's take curve 2 and let us also take some theta value here, right? Let's denote it as theta x. So for a particular theta x, there will be two beta values, right? So if you draw this dotted line in the y-axis, yes, yes. So welcome, Ginny, right? So I am just explaining the theta beta m relation, right? So what I was telling is that, so I just discussed the theta max, right? Theta max in the theta beta m relation. So I was telling is that for a particular Mach value, for a particular Mach number, we have a maximum value of theta beyond which we cannot go. So if you see this particular diagram, this corresponds to the different angles that we are uh, concerned with, right? In an oblique shock case. So these are two angles are beta and theta. So beta is the shock wave angle and the theta is the deflection angle. So if we see these two angles in this theta beta m curve. So this is, I was telling that. So if I have drawn these four curves and I have named them as 1, 2, 3, and 4, right? So if you see curve number 4, right? If you see curve number 4, so it has this particular point beyond which the theta won't move further, right? So this essentially means that when we are solving the theta beta m relation, in that case, we won't get any solution beyond this theta. So if we increase the theta beyond this, we won't get any solution for beta, right? So this is any real solution for beta. This is the meaning of this particular curve, right? And then after that, after discussing this theta max, right? So I was discussing the two solutions that correspond to a an oblique shock case, right? So if we have some flow moving at some Mach value, it is moving and it is deflected towards itself, like is the case for oblique shocks. So in that case, I was telling that let's take this curve 2, right? And I took a random theta value of theta x, right? Just for explanation. So if I draw this theta x, this on the y-axis, if I draw this theta x, so if I see that, or we see that it cuts this curve to at two points, right? So let's write it as A point and B point, right? So it cuts this curve to at 2 points, which are A and B, right? So A will correspond to the weak part of this oblique shock, and then there is B where the this theta x cuts the B. In that case, we get this strong oblique shock, right? So for this weak shock, the beta will be lesser, and for the strong oblique shock, beta will be greater, right? The shock wave angle will be greater. This is, please note that this is for a specific theta value only. The theta remains same, but then there are two betas related to that particular theta value, right? So these are the main takeaways from this theta beta m relation, all right? And one another point we need to uh, keep in mind is that when we move from this, if I have this type of graph in my hand, and if we move from this left to right, right? So if we move from left to right, then there is increase in Mach, right? Increase in Mach value. So for the curve number 4, the Mach will be greater than the curve number 1, and in that case, the repercussions are that the theta max increases with this increase in Mach, and various other linked repercussions related to this particular thing related to this particular curve when there is increase in MR. But in the we shall also see a few questions related to this thing, and that will clarify it more, right? But then we shall see it later when we see the question, right? So we leave the discussion for the later stage in this particular session in relation to this particular topic, right? So there are few more 2-3 things that I can discuss, but because there are questions related to that, conceptual questions related to that, so we shall see that during that time only, right? Okay. So theta beta m relation I have discussed, right? So there are inferences related to that. So based on the discussion I have done, so we can like get hold of what is being discussed in that particular topic, right? And if you have particular question, some particular question or specific question, you are free to ask, right? All right. And then there are these oblique shock property relations. So we saw these relations in the previous lecture also. For example, mn1 equals to m1 sine beta, something like this, right? So such type of relations we have discussed in the previous lectures, previous weeks content, right? So for this particular session, we can skip that, right? Or if we require sorry, or if we require those formula for our current discussion, so in that case we can refer to that, right? Sorry. All right. So moving ahead, right? So then there is this lecture 17, where the expansion wave theory has been discussed, right? So essentially what has been discussed is just the revision of the expansion waves that were discussed in week 6, right? And then same is the oblique shock theory, right? So that has been just revised in this particular introduced, or just kept as introduction for the later topics of this lecture, so which are like supersonic flow over wedges, then there are supersonic flow over cones, right? Then there is also one more topic, supersonic flow over blunt body. So these are the real time or the real time examples of these concepts, expansion waves and oblique shocks. So these have been discussed in lecture 17, right? So if you see 17.3, so this is about supersonic flow over wedges. So what a wedge is, right? So you should be clear. I believe you should be clear about supersonic flow over wedge. So it should be clear that what a wedge is, what a cone is, right? What a blunt body is. So wedge basically is nothing but something like this. So it's not a cone. So don't mistake it with a cone, right? You can imagine it like this, right? So it's 2D, right? So a wedge is it's not like this. It's not like this. In that case, it would have been a cone, right? It is this way, right? So this is a wedge, right? So if this is the center line, right, and flow is moving in this direction, so this is our wedge, right? Okay. So if we draw a cone on a paper, so it will obviously look like a wedge, but then there is difference between a wedge and a cone. So that we must know, right? So then there is case of attached and detached shock on a supersonic vehicle, right? So what is an attached case and what is a detached case, right? So from this theta beta m relation, as I was discussing, that there is some limit of theta, right? So if you go beyond this maximum value, in that case you don't get a solution for oblique shock, right? So in that case, what happens is that we get a shock that detaches from this your body. So if this is your body, so it will not remain intact with the body as was the case with oblique shocks. It will detach from it, right? So this in case of these blunt body or cone, right? So it come out as a bow shaped shock, right? And we uh, name that shock bow only, right? Bow shock. So from its appearance only, we give this shock its name, that is bow shock, right? Then this was about what is attached and detached, right? So if theta, it's just about theta m. So if we are within the theta max, so we will get an attached, and if theta max we have this deflection angle greater than theta max, in that case we will get a detached shock, right? So then there is this symmetrical wedge, right? So what I just drew a few minutes back, that is a symmetric wedge. So in that case, both the angles will be same, right? So these two angles, this theta 1 and theta 2, these two angles will be same, right? So this is a symmetrical, right? And then there is this finite wedge, right? Uh, this is also similar to wedge, but then it is that we are not um, in this because this wedge is uh, in its later part, it is linked to some other shape object. That's why we are calling it a finite wedge, because we have restricted this wedge to some length. For example, if this is a wedge, so this is a cylinder, right? So this is a case of a finite wedge, right? So if this flow is moving in this direction, this is a wedge, and this is a cylindrical shape. So because this particular length is finite, so we call it a finite case, right? Right. So I have written it cylindrical here, but because it's a wedge, it won't be cylindrical, right? So some shape, all right. Let's say some shape. So basically, this is what a finite wedge is, right? And then there is a unsymmetrical wedge also. In that case, unsymmetrical wedge, right? Unsymmetrical wedge basically is for the case when we have a flow which is at some angle to the to our flow, right? Right. So I can draw this particular thing, right? Diagram, but just remember that when we have this, let us say we have, right, flow in this direction, right? And this is the this axis of this cone, right? So if this is the axis and this is the flow direction, right? So we see the angles of on the both sides of this cone or wedge, right? So if this is theta 1 and this is theta 2, and if theta 1 is not equal to theta 2, in that case it's an unsymmetrical wedge, right? So if we know that this the body we are designing is will be at some angle to this flow, right? It is at some angle of attack to the flow. In that case, we prefer such kind of shapes, right? All right. All right. So then there is supersonic flow over cones. So one important uh, uh, point to note is that if we take the same max, right, if we take a same particular specific Mach value, so if we compare the strengths of the oblique shocks that we obtain in case of a wedge or in case of a cone with same this deflection angles, right? So the strength in case of a cone will be less, right, in comparison to this wedge. And we call this particular phenomenon as this relieving effect, right? 3D relieving effect, as, right? So by virtue of this, the change in the behavior of this oblique shock we see, right? So this is about uh, cones, right? As far as the supersonic flows are concerned. All right. Then there is this shock expansion theory. So in this particular topic, what we have discussed is shock expansion theory. So we study a diamond shape, right? Sorry. We study a diamond shape, and let's suppose flow is moving in this direction. So in that case, this particular phase will experience an oblique shock, and this particular these particular edges will experience expansion waves, right? I hope there is no doubt in this that why uh, oblique shocks are uh, being witnessed in a particular corner, and a expansion wave is being witnessed at a particular corner. I hope there is no doubt in this particular thing, right? So this is a diamond shape, right? It's a 2D diamond. 2D diamond shaped waveform, right? Okay. So in that case, we take help of expansion, the shock expansion theory to uh, better explain the flow and various uh, parameters related to the flow that we are interested in. So we try to solve that using this particular shock expansion theory, right? The shock is for oblique shock and then expansion is for expansion waves. All right. So, and then there is also this wave drag related to it, right? Wave drag related to it. So because across this oblique shock, this there is, let's say, if this is P1 and this is P2 and this is P3, so there will be a drag because of these pressures, right? Because across this oblique shock pressure increases, and for expansion waves pressure decreases, right? Static pressure decreases. So this pressure difference of P2 and P3 creates a push, right? Uh, it creates a like a drag to this particular foil, the airfoil. So that we call as wave drag, right? So this is about the shock expansion, sorry, shock expansion theory. And then there is a supersonic flow over blunt body, right? So one important thing in it is that if we see a blunt body, right? So in front of this blunt body, right? I haven't drawn it. So in front of this blunt body, there is some region where this Mach is less than 1, or say Mach is supersonic if this is the flow direction, right? And this is our blunt body, right? So these are shocks. Nothing but shocks. This is also a shock and this is also a shock. This is also a shock, right? So this is subsonic. It's M supersonic, right? So there is some region in which this flow will be subsonic in front of this blunt body, and then at later stages this there is this oblique shock, uh, there is this expansion, right, takes place, and we get this oblique shock. Otherwise, if you see the only the front part, then it behaves like a normal shock, right? So this is about the blunt body, right? Okay, right. So mostly I have discussed the things, right? The topics that have been covered in week seven's content, right, from the lectures. So now we shall move on to our questions, right? Right. So, so let's see our first question. So this question is based on oblique shock waves, and the question says this: which of the following statements is correct? So please read these statements carefully and let me know which statement is correct. Yes, Ginny, if you are there, please try to answer this. All right, no answer. All right, so let's see these statements one by one, right? So the first statement says is that the
A,
oblique,
sorry, D.
uh, you say D, this option or B, last,
A, A.
A1.
Hmm.
Okay, so there is confusion. Okay, so let's just see these statements one by one, right? So first says that oblique shocks are curved and then inclined at an angle upstream of the flow, right? Then there is oblique shocks are curved and inclined at an angle downstream, right? So here is straight and downstream, right? Here is straight and upstream, right? So I have played with these four words only, right? Curved, upstream, downstream, and straight. So what you see is unless yes, there are cases where oblique shocks are curved also, right? So it can be, if I say either A and D, right? But while we were this discussing oblique shocks, so we have seen that oblique shocks, if you see, are in case there is this wedge or the deflection is uh, not finite. In that case, the oblique shock is straight, right? And then obviously it does make an angle with this upstream, right? So upstream thing is correct, but then whether oblique shocks are straight or curved, so unless specified that there is this finite uh, deflection, right, finite wedge, in that case uh, the oblique shocks, if you see, are generally straight, right? But then obviously if there is this finite case is there, then oblique shocks uh, are curved also, as has been given in the content of lecture 17, I believe, right? But then, okay, A is also correct, but then I have given here D option, right? So both can be both these options are, I believe, correct, right? Okay, so this was question number one. So let's just add A also here, right? Right. Okay. Right. So let's move on to next question then. Right. What is the relation between the angle that an oblique shock makes with the flow and Mach angle? Right. Right. Yes.
It should be higher. Um,
Should be higher. Okay.
C.
See, which
Uh,
one should be higher? Mac angle should
uh,
be higher, or
back
the
angle should be less.
Mac angle should be less, right? So
Yes.
from that
Okay.
statement, yeah,
Yes.
B is correct, right?
Ah,
So
yes.
yes, yes. So what's the formula for this? You see question number 2, right? So sorry, sine inverse of 1 by m, right? So this is this Mach angle relation. But then if you see these oblique shocks, right? So beta will be always either greater than m or equal to this mu, right? And if beta is equals to mu, in that case, we call that as Mach wave, right? And if it's greater than mu, in that case, it's an oblique shock. Also, we know that beta is this Mach wave is the weakest form of a shock wave, right? So these are some few points that we must remember, right? All right. So moving on to next question. Okay, so B is the correct option, right? You're right. And then let's move on to next question. So this question is on previous question was on which oblique shock waves only, right? This question was from oblique shock waves topic. So now this topic is on theta beta m relation, right? So this is theta beta m curve, I should say. Okay. So the question says that with the increase in Mach, what happens to the maximum deflection angle? Yes. Yes. If you see this diagram, right? From here, it can be figured out. So with increase in Mach number, what happens to the theta max? You should be clear in mind that what theta max is, the maximum deflection angle, right? And then it would be easy to answer this, right? So with increase in Mach number, there is increase in the maximum deflection angle, right? So we can deflect the flow further, right? With this increase in Mach number. So if you see this diagram, so if you see these curves 1, 2, and 3, 4. So this is theta max. This point is theta max 1. Theta max 1, right? This point is theta max 4, right? For fourth curve, I mean. This one is for theta max 3, right? And this point is for theta max 2, right? So in these cases, for the curve 4, Mac value will be the highest, right? And for the curve 1, the Mac value will be the lowest, right? So what happens to the maximum deflection angle with increase in it increases, right? So option A is correct, right? So if you see the option, yes, option A is correct, right? So I believe this is clear, right? So you need to have hold of this theta beta m curve. So if you remember this curve, so the trends of this curve, if you know, so you are good to go to solve this type of question, right? Okay, so let's move on to next question. All right, so this again is on theta beta m curve, right? Okay, the question says for a weak oblique shock with the increase in max with the increase in Mach, what happens to the shock wave angle? So the question has given weak oblique shock, then there is increase in Mach. What happens to the shock wave angle? It is asked about beta, right? Okay, all right. So this basically is right. Right. So this part is from the inferences of this theta beta m curve, right? So the theta beta m curve, there are 4 inferences. So this question is from there only. So if you increase the this Mach number, in that case, for a particular theta value, right? So if you see this diagram, right? So if you have kept theta constant and you are increasing Mach value, right? So in that case, what happens is that this beta value, it starts coming towards this your wall, this deflection wall, right? It starts coming close to this, sorry, this deflection wall, right? Right. So even if you see this particular theta beta m curve, or because it's too much occupied, I'll draw another curve, right? Question 4. So here is beta, here is theta, right? So it is something like this, thing like this, something like this, and something like this, right? And in this direction, m increases, right? So for a particular, if you see these are, let's name these curves as 2, 3, and 4, right? So if you take a particular theta value, right, and the question says that we are concerned with weak oblique shock, right? So weak oblique shock is this, if this line corresponds to the theta max, right? If this corresponds to theta max, let us suppose this line corresponds to theta max. So below this line we have this weak oblique shock solution, right? Solutions, right? So we are concerned with these points only, right? So for curve 1, this is beta. This is beta 1. And for curve 4, this is beta, right? This is beta 4. So it is very much clear that beta 4 is less than beta 1, right? But Mach for 4 is greater than Mach for 1, right? For the curve 4, Mach is the highest, right? But if you talk about the beta for a particular deflection angle, so it will be the lowest of all. I hope this is clear, right? Yes, Ginny, this is clear or there's some doubt in it?
It's clear.
Okay, right. So it decreases, right? With increase, and so if we go from 1 to 4, the beta value has decreased. So option B is correct. So let's see another question. All right, it's on theta beta m curve, right? So the question says, yes, about the bow shocks.
D.
B for ball,
D. Last one.
D,
Curved and
curved and detached, right? Okay, yes. So as uh, I had mentioned it, right, about bow shocks. So bow shocks are cases when the theta max value is greater, when the theta value is greater than the theta max for a specific Mach number. In that case, the shock detaches, and what we get is a detached shock or a bow shock, right? So yes, you're right. The answer to this question is D, right? Okay, all right. Okay. So just because it's 4 p.m. already, so let's wait here for a while, 5 minutes, and then we shall continue the session, right?
okay.
Okay. Okay, then let's continue with the session, right? If you are there. Right. So next question, question number 6 is uh, this question again is on theta beta m curve, right? The question says that when there is a 0 degree flow deflection angle, the the strong shock takes the shape of a normal shock. Yes. So deflection angle is 0. In that case, the strong shock takes the shape of a normal shock. So whether this statement is right or wrong. Yes, Ginny, if you are there. No response?
Yes.
Yes. Whether it's true or false?
It's true, I think so.
I think it's true. Okay, so let's see. So if you see this graph, this is 0 degrees, this is 90 degrees, right? And this is some value. Let's take it as, because in lectures it's given 50 degrees, so I'm just writing 50 degrees. It needs not to be 50 degrees, right? It depends on the Mach value. Just for the sake of giving it a number, I'm writing it 50 degrees, right? So question number 6, right? So the question says that this deflection angle is 0 degree, right? So it means it's here, right? In that case, if we have some Mach, okay. So let's say curve 1, right? So curve 1 cuts this y-axis, this theta equals to 0 line. It cuts the theta equals to 0 line at these points, right? The points, right? I'm emphasizing on. So this is for curve 1, right? So we know that below this theta max line, this solution is for weak oblique shock, and this is for strong oblique shock, right? But we also know that when beta equals to 90 degree, it's a special case. Special case of what? Special case of normal shock, right? Right. So if there is no deflection or 0 degree deflection angle is there, in that case, this strong part of this solution is essentially a normal shock, right? So if you see the question, when there is 0 degree flow deflection angle, the strong shock takes the shape of a normal shock, right? So this is true, right? So answer is correct. So let's see next question. So this question is from theta beta m curve controlling parameters. So this, as this heading also, subheading also suggests, so we are trying to control the, if we wish to control the behavior of an oblique shock in terms of its uh, shock wave angle or strength, then how do we do that? So this subheading caters to such thoughts, right? So question number 7 says that when the normal component of Mach number ahead of shock wave increases, right, the strength of the shock wave also increases. So whether this is correct or not.
Yes, true.
Okay. Yes. So okay. So this is question number 7. First, okay, I'll give it a new page. Because in the previous this session, I wasn't able to discuss these components of these oblique shocks, right? So I'll do that in this session because this is related to components. So I believe it's important that, let us suppose this is our oblique shock, right? At some angle beta, right? And this is our flow, right? This is our flow, right? So and it is being deflected by some angle theta, right? Because if let's say this is the uh, wall, right, where there is flow, right, and then we are deflecting it with some this wall which is at theta angle, so this direction above will also be in theta direction, right? So this is what I have written, nothing else, right? Now I'll just draw the components, right? So if this is M1 and this is M2, right? So what I'll do is I'll first draw a normal. Right? So I'll break this M1 into two components. One will be the normal component with respect to this oblique shock, right? When I'm saying normal, it means it is normal to the oblique shock, and then there is one component which is tangential to the oblique shock, right? So this is our oblique shock. So this and this, right? So this is tangential part, and this is normal part, right? And then same is the case for M2 also. So one is this component, right? And one is this component. So there are two components. This is MT2, right? Tangential part in the downstream section. And then this is MN2. This is the normal component. So this is about the components of these Macs, right? Mach numbers in the normal and tangential directions with respect to an oblique shock, right? So if we increase this uh, normal this value, right? Uh, Normal component of the oblique shock upstream of this Mach number. In that case, obviously the strength of the shock is going to increase, right? Right. Okay. All right then. Let's keep this expression in mind, right? Because same is the case for these normal shocks also, because in that case, if we increase the Mach number, with that increase in the Mach number, the strength of these shock waves also increase, right? From the mathematical expressions, we can just figure this out, right? So same is the case for oblique shocks also, because this normal part is nothing but uh, it replicates the behavior of a normal shock only, right? So this is true. Right. So next is on supersonic flow over wedges, right? So here the question is concerned with the symmetrical wedges. Yes. So there is a statement, right? The statement in question number 8 says that pressure jump across the oblique shock induces wave drag. Whether this statement is true or false. Even in the supersonic vehicles also, when we are designing or when we are keeping in mind the wing shapes or the fuselage shape or the nose shape, we have a particular reason behind that, right? So one of the reasons is to reduce the wave drag that this particular aircraft is going to encounter when it is cruising at supersonic speeds, right? So that is like about the wave drag. But here question says that pressure jump across the oblique shock induces wave drag. So is this the causing agent for a wave drag, or there is some other phenomena or phenomenon that causes this wave drag? Yes. What do you think?
Answer is A.
Answer is A. So that is very much correct, right? So because across this oblique shock there will be increase in static pressure, right? So this static pressure will, as I was just recently discussing this diamond airfoil, diamond shaped airfoil also. So there also happens the same thing only, that across this oblique shock the static pressure increases, and this static pressure pushes this object backwards, right? Because the surrounding pressure is no match to the this pressure increase in static pressure across this oblique shock, and which eventually leads to this push in the direction of the flow, right? Which is, or you can see it this way, that it is against the this force is against the motion of a particular object, right? Because in these if we see aircrafts, right? So in that case, the motion is relative. Uh, in aircraft, it's not that we have a flow, right? It's not like we simulate in wind tunnels, but there the aircraft is moving, right? So in that case, there is relative flow, right, with respect to aircraft, but the cause of that relative flow is the movement of the aircraft, not the movement of a particular air or gas, right? So it hinders, that oblique shock hinders this particular movement of an object or aircraft, right? So A is the correct answer, right? Okay, let's move on to the next question. Supersonic flow over wedges, right? In case of a symmetrical wedge, when the semi-wedge angle is higher than the maximum flow deflection angle, the flow in the vicinity of the nose is supersonic. So whether this statement is true or false, right? Yes. So flow in the vicinity of nose is supersonic. So here what it means, that if this is the wedge, right? So this is the vicinity of nose, right? If this is the flow. So whether this thing is true or not. Obviously, this is for a supersonic case. Rm is greater than 1. So does it happen that the flow here also in this region also the flow remains supersonic, or there is some other thing that happens? Because for higher than the flow deflection and maximum flow deflection angle, there will be a bow shock, right? I've also discussed this here also. If you see here, see. So here I have discussed that this part behaves as a normal shock region, right? And in that case, in the vicinity of the nose, right? So this is a nose. In the vicinity of nose, it will be, yeah, flow will be subsonic, right? M will be less than 1. But the question has been put forward in this way, that nose is supersonic, which is which we know is not true, right? So it's false, right? All right. So moving on to next question, the supersonic flow with cones. So this is talking about cones, right? So for a specific Mach value, the static pressure rise across an oblique shock is higher in case of a conical shape when compared with the. So a specific Mach value has been given. The static pressure they have asked, the rise in static pressure that happens across an oblique shock. So they have a question on that. So they are saying that this is higher in case of conical shape when compared to wedge. So static pressure rise in case of this cone is higher, and in case of wedge is lesser. So is this true or false? Yes, any idea? No idea.
No.
Okay. So I was discussing this earlier that for this cone shape, we have this 3D relieving effect, right? And because of that, the strength of oblique shock in case of strength of oblique shock, right? In case of cone is lesser than wedge, right? Because of 3D relieving effect. Because if you see in wedge it's 2D, right? We have this only, but then in case of cone it's like this. So there is some kind of relieving in the flow because of this 3D effect, right? Well, it's not just this shape. It's in all possible directions. This uh, wedge shaped thing is right, which is in 3D is a which we call as a cone. So in that case, the strength is less than this for which is what is for wedge, and because of that, if you see this question, the static pressure obviously for where the strength is higher, there will be the static pressure will be higher, right? There will be more compression in that case. So which is in this case for wedges, right? So for wedges, the pressure rise will be higher in comparison to the cones, right? So in case of a conical shape, no, which is, this is false, right? It's not for conical case, but it's for the wedge case. If we take a particular deflection angle, right? If we keep the theta same for both the shapes, a wedge shape and a conical shape, right? Right. So moving on to next question. Supersonic flow over cones. Okay, this is again on cones, right? For a specific Mach and deflection angle. Okay, so particular Mach is there and particular deflection angle is there, right? And they are talking about a cone, right? So in that case, the shock wave angle in case of a cone is smaller than for a wedge, right? Yes. So whether this is true or false. So there are two cases. So here also we have to see in terms of this strength only, right? Let's say this is wedge and then there is this theta is same and then there is cone, right? Then there is cone which I'll draw the same way, right? But then it's a cone. M is same and theta are same, right? M wedge, M cone. Theta W is equal to theta C and M wedge and M cone and M W equals to MC, right? This is given. So the shock wave angle beta that you get. So the shock wave angle in case of cone is smaller than for a wedge. Whether this is true or false. Okay, so this question is from slides only, right? So it's well written, well mentioned there that for this specific value of Mach and deflection angle, the shock wave angle in case of a cone is smaller than that of a wedge, right? So beta for this case, if you see beta for uh, it has been this one example has been given numerically, right, of beta, in which I believe there is beta for cone is 39 degrees and for this wedge is it's around 50 degrees, something like that is there, right? Because with increase in beta, there is increase in strength also, right? Because when we see, right, when we say that if we increase mn normal component of this oblique shock, it increases the strength, right? So that is true, it increases, but mn1 is also m1 sine beta, right? So either you increase m1, by that you can increase the strength of oblique shock, or you increase beta, right? So we know that for the case of wedge, the strength is higher, right? And for the case of cone, the strength is lower. For same theta value, for the same deflection, for the same theta value, the strength for wedge is higher in comparison to the cone because of the 3D relieving effect, right? So if strength is higher, that means the beta will be higher. So beta for wedge is, from here we can deduce that beta for wedge is greater than beta for cone, right? Yes. So it means beta for right, yes. Or we can say beta for cone is less than beta for wedge, right? So which is also our statement of this question number 11. So this statement is true, right? So this statement is true. Okay. So moving on to next question. This is again on supersonic flow over cones, right? So the question number 12 says that for a specific Mach value, the maximum deflection angle in case of a cone is smaller than for a wedge. So the question says that we have some Mach value, right? And then there is maximum deflection angle in case of cone. So these questions are talking about comparison only. So maximum deflection angle in case of a cone is smaller than for a wedge. All right. So now they are talking about theta max. So for which case theta max will come early and for which case theta max will come later in terms of the theta angle, right? The deflection angle. Yes. Okay. So from this, if we see cone, right, and if we see a wedge, see this is wedge and then cone, right? In terms of strength, if you see higher, right? This is low. And then if you see beta value, right? Beta is for this is high, for this is low, for for same deflection angle, right? Right. And then if you see theta, right? So from this particular theta beta m curve, if you see, so what do you see here is that with increase in Mach, there is increase in theta max value, right? With increase in m increases the theta max values, which essentially means that with increase in the strength of the this uh, with increase in the strength of the shock increases the theta max value, right? So here the strength is decreasing, right? If we go from a wedge to a cone, the strength is obviously decreasing, right? So in that case, the maximum deflection angle for cone should be smaller than for a wedge, right? Yes, because the strength is decreasing. Strength is decreasing means this we are moving in this right to left direction in theta beta m case, right? So it should have decreased, but somehow the content of this slide says that this is theta, this theta value increases. So I'll just check this again, this question, right? There's some confusion in this question, right? Because answer says it should increase. So I'll just look into this, right? All right. Anyways, okay, let's move on to next question then, right? I shall clarify this in next session. Okay. So there's question 30 on this supersonic flow over blunt body, right? So in case of a blunt body near the nose, the shock is normal to the free stream and gradually becomes oblique away from nose, right? So near the nose, shock is normal to the free stream and gradually becomes oblique away from the nose, right? So we have discussed this, right? So near this nose, it's normal, right? Normal shock and gradually becomes oblique as it moves away from nose. So this is nothing but this case only. Well, let me show to you. So this case, right? Where we have discussed this wave drag. I hope this is visible on your screens, right? On your screen. So near this, because it's acts as normal shock, so we get the subsonic values, and then as we move further down, right, away from the nose, so in that case, this acts as a oblique shock, right? So this is about a blunt body, right? Okay. So if your nose is like curved, right? So it becomes a blunt body, or if it's sharp, then we call it a cone, right? So that's the difference between a cone and a blunt body. All right. So now moving on to numericals, right? So this is true, right? So please note down this data and just let me know when you are done, right? Noting down this data, and then we shall solve these questions, right?
Okay.
Though I have not solutions to these numericals, but I have the steps like how to do this. So we shall do this together exercise, right? And let's see
Okay.
how the answers come out.
It's done.
Done. Okay. Just
Yes.
give me a few seconds. Okay. All right. So these questions are from oblique shock property relations, right? So question one is find the static pressure at the downstream of the flow. So this is about this question is basically about this oblique shocks only, right? So let's see how can we find this. The question says that we need to find P2, right? Downstream, we need to find P2. But what has been given in the question is right. This is our question number 14, right? Solution. So here we have, all right, I'll just not write what has been given, right? So what we first we will do is, because we need to find P2, we need to find, right? But the question has given P2 by P1, right? Is given 3.4, but then we don't have this uh, right. So this P2 by P1 linked to some value, right? For some Mac, it is given, right? For this Mac P2, I have kept this question very straightforward, right? So examiners might confuse you on this, so you need to tackle that. But for this session, as far as this session is concerned, I have just kept it this straightforward so that you know the steps that as to how to like proceed for such type of questions, right? So for MAC of 3.11, P2 by P1 is given, but we have been asked P2, right? And we have been provided with V1 also, right? We have not been provided with M1, right? So we cannot come to any conclusion as to whether we can use this P2 by P1 to find P2 uh, asked that has been asked in the question, right? So what we will do first, we'll find the MAC, right? So for Mac, we need to, step one is we need to find A1, right? And how do we find A1? We will use gamma T1, right? So T1 here is given, right? Gamma is also given 287 into T1. T1 is 295, right? If you take out the root, what you will get? Right, you get this, right? And if you find the M1, what do you get? V1 by A1, which is nothing but 1070 divided by 344.28, which comes out to be 3.1079, right? Which is 3.11 if we approximate it. Yes. So question also gives you this M 3.11 specific P2 by P1, right? So P2 by P1 is given as 3.4, right? Implies P2 equals to 3.4 into 98 kilopascal, right? So if you multiply it, what do you get? Yes, 333.2 kilopascal, right? So this is your P2 value. This is question number 14 solved, right? Any doubts?
No.
No. Okay. Then there is question number 15, right? So question number 15 says find the downstream temperature, right? So because we have the MAC, so we can just find out T2 by T1 for MAC 3.11, right, is 1.5, right? Implies T2 equals to 1.5 into T1. T1 is, what is T1? 295, right? So this comes out to be right, Kelvin, right? So this is the static temperature increase across a shock, right? Are we good up to this point? Actually, I have done one mistake, right? What I have done is, because this should have been, I have calculated M1 here, right? Because you cannot calculate for this, right? You need to find MN1, right? Just give me a second. So this is 3.11 into sine of 40 degrees. So this is 1.99. So in this question, in case of just, you need not to change the whole question, right? Just in case of here 3.11, you need to write 1.99 or 2, right? Else the question remains same, right? Because when we are talking about P2 by P1 in this relations also, right? In the formula for P2 by P1, we are basically concerned with Mn1, the normal component of this particular flow, and not the whole part of this particular flow, right? in all the in if you see in even T2 by T1 also, or row 2 by row 1, we are concerned with the normal component of this max. So we need to see this normal component, and against the normal component, what are the values. So we need to target those things only, and not the this whole MAC of this flow, right? Only the normal component. So right.
So for all problems, we need to consider this M1 only.
Yeah, only MN1 only, and not M1, right?
So M1, the data will be given whenever
Yeah,
problem
yeah,
is
yeah,
asked.
yeah, 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 yeah.
Okay.
So because when you say this, when you are finding out this pressure across the oblique shocks, right? So this particular P2 by P1 can be found out just based on this MN1 value only, right? This MT1 is not making any effect on this pressure rise across this oblique shock. So the value of MN1 will be sufficient to uh, find the this ratio or the pressure rise across the shock, right? So same is for this temperature ratios also, right? So the T2 by T1, take it as it corresponds to 1.99, right? All right. Okay. And if you see next question says that find the flow deflection angle, right? So how do we find the flow deflection angle, right? It is asking us to find theta, right? So what is theta? You don't know, right? So what we will do is we have Mn1, we have P2, we have T2. So because now you see, if you see this, you need to have a good hold on this particular diagram, right? From in question 7, I have explained this, right? So if you see, right, here, this theta, just angles I'm telling you, this angle is beta, right? And if you see this angle, this is because this is pi by 2 minus beta, because if you take this angle and this angle, they both add up to 90-degree, right? So if this angle is, I believe these are called alternate angles, if I'm correct. So these are taught in very initial geometry classes, right? Maybe from sixth to 10th standard. In those classes, I believe this is taught, right? Uh, though I don't remember it very, like, I very stark memory I don't have of this particular thing, but yes. All right. So because this is beta, right, and this is 90 degrees. So in a triangle, the sum is 180 degrees, right? So because this is pi by 2 and this is pi by 2 minus beta, so this will also becomes beta, right? Because pi by 2 and plus pi by 2 minus beta plus something equals to 180 degree, right? So if you take this as beta, if you, this is one angle, this is two angle, if you take it as beta, then it whole comes out to be 180 degrees. So this is beta, right? Right. And if you see this whole angle, because this whole angle is opposite to this angle, this particular angle, this angle, right? This angle. So these are from same lines, right? If you see the lines, if you see this line, right? If you see this line, and if you see this line, right? So these two angles, this angle and this angle, they are opposite to each other, right? Just from the two lines, if you from two lines, if you get two angles, right? If this angle is the first angle and then there is one angle here, down here there is one another angle. So these two angles will have same value, right? So this is also a concept from geometry. So this whole angle will be beta, right? But then if this small angle is theta, so this angles come out to be beta minus theta, right? Right? This is clear, I believe, or no?
Okay.
Yes. So I'll just rub this, right? So I'll just directly write it here. So this is theta and this is beta minus theta, right? The whole angle is this whole angle, opposite angle is beta, but then this particular angle is beta minus theta, right? So what we will do is we will find the tan of this beta minus theta, right? So we will find the velocity of this component and the this component, the velocity of this component, right? The velocity of this normal component, the velocity of tangential component, and this way we will find the tan, and from the tan inverse we will find then beta minus theta, and because we know beta, we can get theta, right? So how much time do we have? Okay, 4 minutes only. All right. So what we will do is first we will find mt1, right? Which is m1 cos beta. This is how we will find this tangential component, right? And then from there we will find the velocity. This is the velocity of the tangential component, right? I'll write this here also. So if this is right, if this is the Mach, in terms of Mach, if we write this is mt1, but in terms of velocity, if we have to write, we will write is omega, right? So or w, you whichever you want to call it, right? And then here also, if this is m in terms of Mach, if this is mt2, then here this is this is omega 2, right? For normal component, we will use u1 terminology for velocity, right? And then this, for this here Mach, we will use u2, right? For this normal Mach, if there is a velocity corresponding to that is being denoted by u2, right? So in terms of velocity, I'm telling you what terminology we are using, right? So here then velocity comes out to be mt1 into a1, right? A1 is the speed of sound that we already have, right? So this way we will find velocity, this tangential velocity, but this tangential velocity is also equal to the tangential velocity downstream of this shock, because the tangential component doesn't change, right? So this is step number 5, right? All right. So leaving the steps. So this is one step, right? So then another step is you find mn2, right? From the table, because this mn2 for you is 0.6 here, right? Across the shock, because for 1.99 it has been given that mn2 is the normal component is 0.6, right? So this is your mn2, right? And then you can find out the u2, the normal component, right? Normal component, how you can find out? From mn2 and a2, right? Because you have this t2 value you have, right? Because you have t2 value, you have mn2, you have a2. From here you can find u2, right? Now you have u2 also, right? And you have this also, w2 or omega 2, right? So the last step in this question is tan of beta minus theta, right? You find tan. Tan is what? u2 by w2, right? From this thing you can find out your this beta minus theta, you can find out. right? And because you know this beta value, so theta can be found out, right? So I believe this is clear, right?
Yes.
Yes, thank you. So then there is last question, question number 17, right? So in that you need to find out this, I show you, find the velocity at the downstream of the flow, right? You need to find the velocity at the, now it's very simple, right? You need just Pythagoras theorem and nothing else, because you have u2, you have w2 or omega 2. So v2 is nothing but u2 square plus w2 square root, right? And you're done with it, right?
Yes.
All right then. So we have completed the questions, right? Prepared for this particular session. And so in conclusion, we'll say that we discussed the week 7 topics from this NPTEL course, Fundamentals of Compressible Flow, right? And then we discussed conceptual questions, 13 conceptual questions, and after that, 4 numerical type questions, right? And this way we came to an end to this session, right? And we will end this session here only, and we shall meet again for week 8 uh, lectures discussion, right? And solving some numericals based on the content of week eight's content, right? Till then, bye bye. All right,
Mm.
take care.
Bye. Thank you.
Yeah, happy learning. Take care. Bye.